Greetings, I'm Zar Christian D. Navarra from section Y16 and I'm here to discuss fractal design's technology. Let me first ask you a question. Do you know what a fractal is?
Let me show you an example. Draw an equilateral triangle, and this serves as the base shape. Mark the midpoint of each side of the triangle and draw 3 lines that connect the marks. This results in 4 new smaller congruent triangles. Then shade the middle triangle. This is now the motif shape. Notice that there are 3 new black triangles, 1 in each corner. Apply the motif shape to each of these 3 triangles. Then continue to do so, and so on, and so on, and so on. A fractal is a never-ending pattern that repeats itself at different scales. Despite being a complex-looking pattern, fractals are actually made by repeating any simple process. No matter where you look or how you look at a fractal, zoomed in or zoomed out, its parts are similar looking and is matching to the original image due to its repeating patterns.
This pattern was coined by Benoit Mandelbrot, a Belgian mathematician in the 80s. He may not be the one to discover the said pattern, but he is the one who explained it. Each part of a fractal would be a smaller replica of the full shape, for each divided parts of this shape are geometric. He came up with the term fractal, for it reminds him of the word fraction. It is actually adapted from the Latin word fractus, which means broken or fracture. One of the 3 properties of a fractal is being self-similar. Despite being different in size, the parts of a fractal object will look similar or exactly like the original shape. Another property is the fractal dimension. Here, the fractal's complexity is quantified through the ratio of the change in detail to the change in scale. And accordingly, the fractal patterns are characterized using the index created by the fractal dimensions. The last property of fractal is iterative formation. Fractals are formed using the iterative process. Series of steps are repeated to produce an outcome, and these results shall undergo again through the said steps. Continuously modifying and improving, the product results into a more complex and intricate-looking patterns. Fractals, despite being complex-looking, is actually very common in our surroundings. We don't notice them, but it is actually everywhere. They are seen in the branches of trees and how it grows its limbs, the trunk being the origin point for the fractal, and each sets of branches that grows from the main trunk continues to also grow their own branches. Eventually, these branches will be small enough and become twigs, and these twigs will soon grow into bigger branches and develop twigs of their own. Another incredible place where fractals are seen is in the circulatory and respiratory system of animals. Well, if you take the human respiratory system, you will see a fractal that begins with a single trunk that branches off and expands into a much more fine-grained network of cavities. Fractals can also be seen in ice crystal formations. Its starting point would be in the center and it expands the shape outwards and into all directions, forming fractal structures in each side. The fractal patterns that are formed is one of its contributing factors that makes each and every snowflake unique. Another example is lighting and electricity, one of the nature's most powerful display of fractals. When electricity passes through a medium that does not conduct electricity, the pattern that is created becomes a fractal. As the current passes through the air, it becomes superheated. Superheating of the air changes its electrical conductivity and allows the current to fragment out. This process repeats for each level of fragmentation, and soon you get a fractal. And next time you eat a salad, pineapple, broccoli, or a handful of other foods, you are actually eating a fractal. Plants and leaves, just like animals, have internal structures that distribute nutrients through a network of fractals. These structures allow for easy distribution of liquids and other life-sustaining materials to travel through the plant and support the life of every cell. Another example are rivers and other bodies of water. They collect, move, and distribute water throughout a landscape. And a fractal pattern forms as water moves from a stream to a river, to a lake, or another large body of water. And as these rivers and other bodies of water are formed, they are also carving out the geographic landscape, which makes the land the bodies of water travel on fractals as well. These are just a few examples where fractals can be found. It can be anywhere, and we sometimes don't notice these graceful patterns that lies around us, and literally within us. Fractals surrounds us in so many ways, in ways that sometimes we didn't think was possible, but here we are, mesmerized into its hypnotizing gaze. Formulas formed through fractals make scientific breakthroughs possible. Because of them, important scientific concepts like how bacteria grow, freezing water patterns, and even brainwaves are understood and studied. However, one application of it may sound unreal to us. Fractals are found here in this thing that we use in our everyday life, the thing that connects people from all over the world, the product of mankind's innovation and continuous invention, the technology. Technology is the application of scientific knowledge to the practical aims of human life. To achieve various purposes of individuals and communities, the knowledge we attain are applied in different aspects through a comprehensive process. And we can't deny that the roles and impacts of technology in both our personal and working lives is ever growing. Technology became a part of our daily life. Through its great advances as time passes, it brought ease and improvement to our lives, from communication, education, business, healthcare, and even entertainment. Technology has changed our lives since then. But how can these two interact and be applied in the real world? Despite being common in our environment, examining fractals in the physical world has its own limitations. Investigating these patterns has many restrictions, for observing such details would be nearly impossible in a molecular level. However, with the help of computers and its technical advancements, it helped us to explore fractals at an infinitely deep level. Fractals are actually derived from mathematical equations, and with the technology's capability to calculate incredible numbers, we're able to traverse these beautiful shapes in an incredibly detailed level. In addition, the computer's abilities are not only used for practical applications to research and build fractals, but also it aids us into using complex fractal equations for various applications in the real world. The exploration of fractals within computers started in the 1960s when Mandelbrot worked at the IBM, or International Business Machines Corporation. Mandelbrot was able to generate and even manipulate fractals accurately due to the computer's capacity and computations. Mandelbrot's work laid the foundation of fractals, and to honor the achievement, the most iconic fractal was named after him, which is the Mandelbrot set. As the use of computers to explore fractals increased, its application into the digital world became in demand. Fractal algorithms are used to compress images in various methods to create realistic images, landscapes, and intricate models that are otherwise impossible with conventional technology. Fractal images are actually being used nowadays to create special effects in various aspects, may it be in movies, games, and even digital art. Fractals have a significant impact on how we think about information and data management. If you consider the way information is organized and structured, it originates with some kind of overarching category. Take Canvas for example. If you observe the left side of the website, there are multiple tabs that runs through the site. And when you click one of them, another set of options will be available. And that would be the same for other tabs. And when you click an option, it has its own set of tabs that has different functions of their own. Each of these topics also has their own set of fragmentation into similar or related subcategories of ideas. While fractals for information are finite, you can see a similar branching tree pattern in the way the information is structured. Eventually, the information will be broken down into the smallest possible modular component about the subject. Another example of a fractal that would be a key in the later example is the Sierpinski carpet. The Sierpinski carpet is a plane fractal first described by Waclaw Sierpinski in 1916. The construction of the Sierpinski carpet begins with a square. The square is cut into 9 congruent subsquares in a 3x3 grid, and the central subsquare is removed. The same procedure is then applied recursively to the remaining 8 subsquares. This fractal was then tweaked by Carl Menger in 1926 in his studies of the concept of topological dimension. The Menger sponge is a fractal curve. It It is a 3-dimensional generalization into 1-dimensional Cantor set and a 2-dimensional Sierpinski carpet. It begins with a cube, and then every face of the cube was divided into 9 squares, like a Rubik's Cube. This subdivides the cube into 27 smaller cubes. The smaller cube in the middle of each face was then removed, as well as the smaller cube in the very center of the larger cube, leaving 20 smaller cubes. This is a level 1 Menger sponge. Repeat the steps 2 and 3 for each of the remaining smaller cubes, and continue to iterate. The second iteration gives a level 2 sponge, the third iteration gives a level 3 sponge, and so on. These shapes was then applied by a radio astronomer named Nathan Cohen to rethink wireless communications by using a fractal antenna. In the 1990s, Cohen's landlord wouldn't let him put a radio antenna on his roof, so Cohen then decided to make a more compact radio antenna by designing it based on a fractal. To his surprise, it didn't just hit the antenna from his landlord, but also outperformed the regular ones. A radio antenna are made for one type of signal, and it usually works efficiently when its length are certain multiples of their signal's wavelengths. In other words, FM radio antennas can only detect FM radio stations, and it is the same for the TV antennas that can only pick up TV channels. However, fractal antennas are unique. Fractal antennas can pick up more signals as the fractals repeat itself, and it doesn't consume much space like the regular ones. Cohen then designed a new antenna, but this time with the use of a fractal called Menger sponge. This pattern is sometimes used in cell phone antennas, for it can receive all kinds of signals. These antennas are smaller and more intricate than the previous ones. It takes up lesser area and truly versatile when it comes to picking up signals. There are various types of fractals present in our world, even outside your planet. I may not be able to mention them all, but they are present in every aspect. Just like its endless patterns, the application of fractals has many possibilities, and we may not be able to explore those parts yet. These shapes are present even before, and thanks to the curious minds of humans, we are able to open a whole new world that is full of potential. Fractals, with the use of proper mediums, would be a great help in numerous ways, may it be technological or even digital advancements. Fractals prove itself to be extremely useful in improving mechanical properties, as well as comprehending phenomenon that occurs in the physical world, may it be the most simplest things to the most complex object imaginable. These patterns are not just the signs that we see every day, but it also holds meaning and secrets that may help us in traversing this vast universe that we live in.